Good afternoon. Welcome to our session, Specifying Camber, Rules of Thumb for Designers. My name's Terry Zwick. I'm a fabricator from St. Louis with Atlas Iron Works and also on the planning committee for this NASCC. A couple of housekeeping items. We ask that you turn off your cell phones and pagers in respect to the speaker. And a reminder that to receive your CEUs or PDFs that you need to be scanned in the back. If for some reason you have a problem with it registering, just come to me and I'll take your name and be sure that your records are updated. The AISC will send your CEU certificates by mail in about 45 days. Our speaker has said if you have any questions along the way, just interrupt her. She doesn't mind. She'll answer questions as she goes through. You don't have to wait to the end. This session was inspired by an article that Erica had written in 2006 in Modern Steel Construction, and she's taken it and presented it before to the Bi-State Fabricators Group, and I'm sure she'll be presenting it again to other fabricator and engineering groups. So Erica Winters Downing is the Great Plains Regional Engineer. Before working as a regional engineer, she had been an advisor for the Steel Solution Center of AISC. She has worked for design firms in Kansas City and Chicago before joining AISC and has a bachelor's and master's degree from the University of Kansas. At this time, I'd like to introduce Erica.
Thanks, Terry. The article that I wrote in Modern Steel Construction, it's not all my knowledge. We gathered knowledge in the Solution Center, so it's kind of a compilation of knowledge that we gathered since the Solution Center was opened in about 2001. But we've also had papers and things in AISC about cambering over the last 20 or so years that are really good, so we just compiled them. I also wanted to thank Dave Wickersheimer kind of put most of these slides together when I didn't have time to based on my article, and then Jacinda Collins, who I saw walked in the door from AISC and the Solution Center, she helped me put together one of the design examples in here from RAM software. So kind of one of the big takeaways from the presentation that I want you guys to get today is that Camber really is more of an art than a science. It's definitely more than checking a box in an analysis software. Also, it's really not addressed in school. I mean, a lot of these items are things that people picked up on the fly in design and over time and trial and error, and have things have gotten messed up in the field. So, here it is for you guys to benefit from. So the things that I'm going to touch on today are the different types of camber that you'll see, methods of inducing camber into beams, effects that it has on connection design, effects that it has on floor slab profiles and what kind of profiles you should choose in your design, and just some kind of general recommendations and do's and don'ts, rules of thumb for cambering. So starting from the basic, camber is a curvature fabricated into a beam or truss to compensate for deflection induced by loads. Camber we usually think of as about the strong axis of a beam if you're bending it about the flanges. Sweep is a term that if you're bending about the weak axis of beam, if you're bending about the web. So why do we care about this? Why are we going to camber beams at all? One advantage is that we're going to use this camber in a beam to reduce framing weight. You can get a lighter section, save some material. You can also reduce your floor framing depth, and especially since working on more of the marketing side of AISC, developers and owners, floor-to-floor height is a big deal to them. Even if you can go from a W21 section down to a W18 section and save 3 inches on your floor framing height, 3 inches if you have a 10-story building is 30 inches, so it adds up to almost 3 feet that you would save on MEP material, facade material, all sorts of stuff. So it is a point of importance for developers out there. Also, whenever I present to architects and engineers, there is this debate. I mean, how much weight do we really want to save? Do we really want to design everything down to the gnat's ass, like people say? Is least weight really least cost? Usually what we like to say at AISC is whenever you get a bid from a fabricator, that bid is made up of two components. About 1/3 of the bid, or maybe 30%, is the raw material that the fabricator purchases. About 2/3, or sometimes 70% of their bid, is the value and the labor that they put into that material. So, I mean, the economy is in keeping things simple, keeping repetition of the same members and connections. You're going to save a lot more money on keeping a simple design than having a lot of different connections and different members. Talking about pricing, it's been very fluid over the last few years. This is a chart that we keep track of at AISC from the 3 main structural mills, and this one, it goes through January of this year. And so the fourth quarter of 2003 is essentially when steel pricing got very kind of fluid and unpredictable. What this chart breaks out is the red part of that price is the scrap index. So that's what steel mills are paying to buy scrap to melt down into steel. The blue line is, the blue part of the price is what it actually costs the mill to roll the steel. So you can see well, I don't know if I can hit this. The blue line kind of goes up at a semi-normal, steady rate. The red line is the one that goes up and down, and that's the scrap index. So, you know, up through the third quarter of 2003, steel was trading at around $400 per ton, which is essentially what it was trading at through the 1970s. So almost 30 years, it was around the same price. In September, October of last year was when it hit its peak of close to $1,200 per ton. In January of this year, it was somewhere around between $900 and $950 per ton. Currently, right now, I honestly don't have a hard price for you for tons of steel. Rolling cycles have gotten so short, and steel is actually, the pricing is varying geographically across the country right now. So we don't have a real hard price for you in March of 2009, and I certainly don't have a price to predict for you for the upcoming months. So to put that into kind of dollars and cents, to try to find out if it's worth it for us to camber something, and this is based off of costs last October when things were at their high of around $1,100 per ton. $1,100 per ton, if you break that down into pounds, so steel beams were costing about 56 cents a pound. If you have a 30-foot beam that weighs 50 pounds per foot, that's a 1,500 pound beam. So that beam would have cost approximately $840. If you call up a fabricator and they say it's going to be $75 to cold camber that beam. The fabricators, when I gave this session a couple hours ago this afternoon, said you can see costs down as low as $35 to camber a beam. I've also been told as high as $200, so it varies greatly. But if you get $75 as a price, that $75 can be equated to about 134 pounds of that beam. So a rough estimate is that the cost to camber that beam is worth about 5 pounds per foot on that beam weight. So if you want to go ahead and camber a beam, it should be saving you at least 5 pounds per foot. So if you start off with a W18 by 60, and cambering only gets you down to an 18 by 55, it's probably a wash and really not worth it. If you can get down to an 18, I don't know if I misspoke. If you get only down to an 18 by 55, it's not worth it. If you get down to an 18 by 50 and save 10 pounds per foot, then it might be worth it to camber that beam. So getting into the types of camber that you're going to run into, there's natural mill camber and induced camber. So let's talk about both of those. This is a photo of a cooling bed at a steel mill. So you can see that the flanges are redder than the web. So this section doesn't cool evenly. The web has cooled quicker than the flanges do. And that's just a natural process, how the beam cools. It cools faster in some areas than others. So when it cools, it might arc up a little bit, and they kind of call that a crown. You might get a natural crown of beam camber coming from the mill. So how do we account for this in our calculations and designs? ASTM specification A6 lays out tolerances for rolling of hot rolled shapes from the mills. ASTM A6 is also shown graphically in our manual in the tables 122 through 129 of the 13th edition. Our specification, Chapter A, references A6, and then also the Code of Standard Practice, Section 5 and 6, references ASTM A6. So here's that tolerance. What does ASTM A6 say? For camber or for sweep, so bending about the weak axis or strong axis, the tolerance is 1/8 of an inch per 10 foot. So if you have a 30-foot beam, the most camber that you could get from a mill is 3/8 of an inch. Usually, the camber you're going to get from the mill is much less than that, and as a rule of thumb, mill camber is usually not a factor in design. Also in our Code of Standard Practice, we note that for beams and trusses detailed without specified camber, the member shall be fabricated so that after erection, any incidental camber due to rolling or shop fabrication is upward. So if the fabrication shop gets beams from a mill that have this natural crown, they're going to set them and work on them so that the crown is facing upward. They're not going to start with a beam that already has a little bit of a sag in it. So whatever natural mill camber is in there is going to benefit you. A beam will not go out to the site already in a sagging position. This part of the Code of Standard Practice is really the only out that a fabricator has of getting out of cambering your beam. If for some reason a beam arrives at the fabrication shop with 75% of its specified camber already in it, no further cambering is required. So I was thinking about this earlier this afternoon, and what would even be a realistic example of when this might happen. Because you're certainly not going to, if you specify 2 inches of camber, I think it would be unheard of to get 1.5 inches of camber from the mill on a beam. So I think you would run into it if you have a relatively long beam and you specify a low amount of camber. So if you have a 50-foot beam and you only specify 3/4 of an inch of camber on that, 75% of that works out to 9/16 of an inch, which is under the acceptable mill tolerance, which would be 5/8 of an inch for a 50-foot beam. So I think that would be one of the only situations you would run into that, is if you have a really long beam and have a low amount of camber on it. So moving on from mill camber to induced camber. Induced camber is camber that's induced in the fabrication shop, rarely done at the mill, usually done at the fabrication shop. Historically, integrated steel mills like a Bethlehem or a Carnegie used to have fabrication operations with them. Nowadays, fabrication is its own specialty item. It's not done at the mill. Cambering used to be done at the integrated mills, and now it's usually done at the fabrication shops. Also, tolerances for induced camber are referenced in our steel construction manual, page 228, and also our Code of Standard Practice, section 6.4.4. So this is what it says in our Code of Standard Practice. For beams up to 50 foot for induced camber, there's a tolerance on the minus side of 0. So essentially, if you call out 1.5 inches of camber, after the fabricator fabricates it and measures it in their shop, it can't have less than 1.5 inches. There's a -0 tolerance. There's a positive 1/2 inch of tolerance. So if you call out 1.5 inches, you might get as much as 2 inches. And it's important to note, and I think on one of the slides, that I do note that camber is verified in the fabricator's shop. It is not verified out in the field. Something else to note too is that there's commonly transportation losses with camber. Losses in transportation may be up to 25% of the induced camber. That's something that you might have to plan for. Like I said, your camber that you call out is verified in the fabrication shop for a beam in the horizontal position. It's not verified out in the field, so there's going to be some losses in transportation. But this is, might be offset because fabricators have that additional 1/2 of an inch of positive tolerance. So if you call out 1.5 inches and they put in 2 inches, by the time it might get out to the field, it might be down closer to 1.5 inches. So those tolerances kind of play off of each other. This is a picture of a cambering jig in a fabricator's shop. There's two pressing rams, which are usually at the third points of a beam. What happens is, this is, say, a 25 or 30 foot beam, so they're going to press it at the third points. It's not a perfect ellipse, and I have a curve shown here in a little bit. If the beam is really long, like 40 feet, they might start this beam at the end here so that a whole bunch is hanging off the bottom and induce a curve here, push it through, induce a curve in the middle, push it through, induce a curve at the end. If you have a really long beam, like 50 or 60 feet, they might induce a curve at 5 different spots along the beam as they slowly push it through that machine. So it really gets into an art trying to get this camber in there. So there's 2 ways of inducing camber in the shop. You can cold camber or you can hot camber. Cold cambering essentially uses that machine I just showed and uses brute force to push the beam past its yield point into permanent plastic deflection. Hot cambering is using heat at various points along the beam length to induce camber, and I'm gonna show both of those here. So cold cambering, here's the background. Here's our stress strain curve of steel. Going up to the first yield point of steel here, this is deflection that would not be permanent. The deflection, once you get past here in the plastic part of the curve, that strain is 10 to 20 times. You can get up to 10 to 20 times the strain that you get in the elastic curve. And then you would go up through some strain hardening and rupture. So when you camber a beam, you're truly pushing it beyond this yield point into the permanent deflection to get that permanent camber in the beam. Now when you specify 1 inch of camber, the fabricator might push it to 2 inches because he has to get past the non-permanent deflection into the permanent deflection, if that makes sense. So if he pushes it to 2 inches, 1 inch of that might be in the elastic range and it'll come back out when he lets the beam off the jig. So he's going to push that beam 2 to 3 times what you need to get. So here's kind of the curve that you're going to get in that cambering jig. So like I said, the rams deflect the beam 2 to 3 times the desired camber, since the elastic deformation comes out as the rams retract. So here's that picture again. I think I showed it twice, but they are going to push it past the yield point into permanent deflection, and then when the rams retract, the deflection from the elastic part of the curve will come out. A common question that I get, since we are pushing the beam into plastic deformation, are we inducing some permanent residual stresses in this beam? And the answer is no. Because the curve is just such a big radius and it's usually just a slight curve, the tension flange is usually almost pure tension force and the compression flange is usually almost pure compression. So when you have that pure stretching and squeezing behavior, that's not going to produce residual stresses in the flanges. The web is a little bit more unclear. There might be some induced in the web, but certainly the flanges are not going to have residual stress. If for some reason you feel like you've way over-cambered the beam and losses in transportation aren't going to take it out and you're beyond your 1/2 inch of tolerance and you need to correct it, you should not correct the beam by putting it back in the camber machine the opposite way. That behavior will induce some strain weakening in the web, and you'll get into that back and forth behavior that will cause fatigue type action. So if you need to correct, you need to apply mild heat in the 200 degree to 500 degree range for a few minutes in the middle third of the beam. And in the session I gave 2 sessions ago, some of the fabricators say that's our general practice, is to put it backward in the camber machine. All I can say is AISC's strict answer is that you should not be putting it backward in the camber machine. If you are going to heat camber, rather than cold camber, you're going to apply heat in the range of 11 and 1200 degrees. You're going to start at one end of the web and go in a serpentine kind of triangle. And this angle here, it should be about a isosceles triangle. This angle should be about 30 degrees. The bigger angle you make, the more camber you're going to induce. And then you're also going to go in a serpentine motion along the flange. So this is how this would look. When this is set up in the fabrication shop, they actually work on it kind of in the upside down position. So when this goes to the field, this is going to be the bottom flange and this is going to be the top flange. They figure they'll get some help from gravity by letting it hang there like that. And it's easiest to work on that top flange there. So this is the flange that they're going to provide heat on, the eventual concave flange. And then the eventual convex flange is down here. It should be noted that heat cambering is really almost 10 times the cost, and I might note this on a later slide, but it's really almost 10 times the cost of cold cambering. And that's purely due to man hours. If it takes you 3 hours to cold camber a beam, it'll honestly take you about 30 man hours to heat camber a beam. And so it's a lot of fabricators, if they feel they can't get a beam to fit in their particular cambering jig, they'll send it to another fabricator down the way rather than trying to heat camber it. You see heat cambering a lot in bridge fabrication shops because those plate girders are a lot of times just too big to be mechanically cambered, and that can take a lot of time to heat camber those bridges. If you heat camber a beam and you need to correct it, it's kind of similar to the others. You can repeat that wedge technique on the opposite side of the member to a lesser degree. How much should we camber? It's good to realize that when we run structural analysis software these days, we're going to get something like 150 load combinations. And our camber is chosen for one of those. So our camber is meant to be, our floor is meant to be flat for only one of these, one out of 150 load combinations. So we need to look at when our loads are applied, how the concrete floor gets leveled off, and how the composite transform section performs. What percent composite are we? So there's really two schools of thought on how much you should camber. The more conservative route really just says you should camber out about 80% of the permanent dead load. And two papers were presented on this at the 1996 NASCC conference that advocated the use of the 80% beam deflection calculations. The basis for those papers was that real connections are not theoretical pins, and they do in fact have some fixity to them. So as a result, the deflection of the member is not that theoretical pin-pin deflection that we calculate. The in-place deflection is usually found to be about 20% less of that of a pin-pin beam. So the 80% of dead load is a result of that. A more aggressive stance, and not wrong, AISC doesn't say don't do this. Some people say I'm going to camber out my dead load, my superimposed dead load, and up to 10% of my live load. If you do that, the guidance given is that the portion of your total camber pertaining to the superimposed dead load and live load shouldn't exceed a half an inch. So if you specify 2.5 inches of camber, only a half an inch of that should be related to the superimposed dead load or live load. So really consider the frequency and duration of your live load. If you're designing a library and it has, it's going to have permanent loads in there for books and things like that, then I might look at cambering out 10% of that live load. If it's just an office floor or a space like this and it's only going to be loaded up once every 2 months, then I probably wouldn't do that. Also think about your finished floor profile. Does the floor need to be completely flat at the end of construction? Or when the construction is done, do you want a slight camber left in your floor so that when the building gets occupied, the floor goes down to level then. So that's something to talk with the architect and with the general contractor about. Also, as engineers, we tend to overestimate our loads for design. We like to be conservative. If I'm designing a floor and I think it's 56 pounds per square foot dead load, I'm going to round up to 60 and do my calculations, and that's actually a bad thing when you're designing for Camber. You really don't want to overestimate your loads. You want to get as an accurate picture as possible of the loads. And also remember that 20% fixity of end connections. Even if you have what we think of theoretical pin connections, double angles and shear tabs, they have some minimal fixity built into them, which AISC does recognize. You know, if you're designing a seismic system and you specify that R equals 3 for seismic, that R equals 3 recognizes that, you know, our minimum pin connections do have some minimal seismic resistance to them. So, you know, these theoretical pin connections aren't 100% pins. They do have some fixity. Effects of camber on connection detailing. Camber is usually performed by the fabricator after the beam has been cut to length and punched or drilled. So for beams that require a perfectly square end, like for example a moment connection, those sometimes might need to be recut after cambering. So I'm going to go through a series of some shear connections and some moment connections and say when it's good or not to specify camber. So this would be a double angle bolted connection. So if you, and this is obviously exaggerated, but if you camber it, here's my beam and this is really not a 90-degree angle anymore. So the fabricator or the erector, when they put that up, is going to kind of have to squish things together to get that connection to work. For a double angle connection, usually it's okay. This connection is going to have enough flexibility and play in the field that those plates will kind of warp into place when the erector puts them up. So this is a decent connection to have if you're going to camber your beams. For shear plate connections or teed connections or single angle connections, these have a little bit less play than the double angle connections. So usually what's going to happen with these is you might wind up specifying short slotted holes on these plates so that when the erector puts them into place, if he has to fit something in, there's a little extra play for him. And that short slotted hole isn't going to bump your connection up to a pretensioned or a slip critical case as long as the load coming in is perpendicular to that slot. So here's some moment connections, and this is where you probably don't want to specify camber on your beam. So this is a connection with a top plate and a bottom plate. Because when you fabricate it and camber it, now my top flange is going to be much closer to the column and my bottom flange is going to be further away. So those cover plates probably don't have the ability to take that differential that they need to take. The web plate, you could probably make it work by using those slotted holes, but it's going to be hard to make that top and bottom cover plate work with a cambered beam. What the fabricator might have to do, and for some reason this isn't working well, but my pointer, the fabricator, if they need an absolutely square end, and this has already been cambered and fabricated, I think I got it. They might have to retrim this beam so that now it's a flat end after it's been cambered. This is another connection where you would not want to camber the beams, kind of a directly welded moment connection. At the top here, that root gap for the weld is going to be scrunched, it's going to be way small, and at the bottom the root gap for the weld is going to be a lot bigger because of this angle. So you don't want to add all this extra weld material down here, and this weld's just going to be scrunched. So this is another connection where you probably would not want to camber that beam. And this is another one where you should not camber, is just an end plate moment connection. If this is less than 90 degrees, the fabricator might wind up having to put some type of a tapered shim plate in there, which they really do not want to do. So that's a bad choice for Camber. This is one moment connection where cambering can work. A seated connection with a top plate that's shipped loose out to the field. This seated connection can take this difference here, and then the top plate is shipped out loose and then welded or bolted onto the top beam flange in the field. Top plate is welded, sorry, not bolted. Floor slab profile. This is always a point of discussion. The guys in my last session said on the West Coast this is really the preferred method, and this is what contractors are doing. And this is what is best for you as an engineer. You want the profile of the slab to follow the curvature of your beam if it's cambered. You want a constant thickness floor slab. What's easiest for the contractor is not to do that. It's easier for them to just set an elevation for a concrete leveler and let it run across the floor. This takes a little bit more care to make this floor profile. So it's not the cheapest thing for the contractor to do, but it's the best choice. So problems for the design engineer, if the contractor just picks that flat elevation, if the elevation's a little high, you might get concrete that ponds at the center of the beam, and the beam's going to start to deflect down. Or if he sets the elevation a little too low, you could wind up with a situation like this where there's a little bit of ponding out at the ends, and you might have those headed shear studs trying to poke through the slab. I think I'm kind of getting into rules of thumb here and some settings for the design programs. Don't over-specify camber, always round down. If you wind up with something like 2 3/8, don't say 2 1/2, go down to 2 1/4. Don't specify camber on beams that would require less than 3/4 inches of camber. Losses in transportation would make it ineffective, and also if you specified a 1/2 inch of camber, it is really too hard for a fabricator to get that little of a camber into their beam. Specify your camber in 1/4 inch increments. Don't specify it in 1/8 or 16ths. It's just not, you can't get that accurate in the shop. Review your defaults in your computer programs. So this is a screenshot from RAM, which is what we use in the Solution Center at AISC. You can choose whether or not you want to camber. We're choosing to only do not camber beams with a span of less than 24 feet. If it's less than that, it probably won't fit in the fabricator's cambering machine. Also, we're saying don't camber beams with a depth of less than 14 inches. Usually beams with a depth less than that are going to have really thin webs, and you might have problems with web buckling on a beam like that. Also, we said don't do it with a beam greater than 44 inches. It definitely won't fit into their machine. Here we had set it at cambering out 80% of the dead load, so we were taking that more conservative route. The camber increment, like I mentioned, is 1/4 inch. The minimum camber is 3/4, and maximum is 2 1/2. You really don't want to go beyond that. And these are some good points that we've picked up over time from various contractors and fabricators. So I'm going to show some pictures. Beams adjacent to members with different deflection characteristics should have their cambers adjusted to transition to each other. What does that mean? So say that, we have this beam here, it's 25 feet, and it has a camber of 1 inch. And then the next beam over is 40 feet long, and we get 1 3/4 inches. Because of that difference, it's going to be hard to lay that deck down and make it fit. So you might want to pick this beam and just arbitrarily say, I'm only going to do 1 1/4 inches on this to help transition laying out the deck over these beams. Be careful of camber differences between beams and joists. and cambered beams and joists adjacent to non-cambered supports. So here, let's say we have a bay of joists, and they all have 1.5 inches of camber, but on the column lines we have wide flange beams. If these joists are cambered, you should probably camber the beams. So don't have camber and then no camber. It would be difficult deck placement there as well. It's also a debate, and I'm going to probably have a show of hands, I'll have a show of hands now, whether you guys camber your girders, because there's really no consensus on this. Some people say it's bad, some people say it's good. So who cambers their girders? Anybody? Who does not? Yeah, that's very true. Also, another consideration with joists, maybe, since those joists have seats, you might have to play with the seat depth if this girder's cambered too, so that might screw things up some. Don't over camber beams with shear studs, because you don't want to, have them poking through the top of the concrete slab. Don't cold camber beams if you're going to be welding on cover plates. That heat from welding the cover plates could mess a little bit with the camber curve that you induced. So here we say members that can be cambered: composite and non-composite beams, and trusses with WT cords or W-shaped cords. These are situations where you wouldn't want to camber. Beams with moment connections, like I showed before, or your frames with the beams that have braces framing into them. You don't want to camber that beam. It's just going to make the brace attachment and gusset plates more difficult. And it's having that support point at the middle point or third points of the beams makes cambering kind of ineffective. Shored construction. This is a picture of a stub girder system, which isn't used too much these days. I think shored construction might be more applicable. We've got a lot of long span deck products out there that can go 25, 35 feet if you have a row of shoring. If you're going to do that row of shoring, it means your steel beam on its own doesn't have enough strength to support the dead load of the wet concrete. So we don't want to camber that beam and make it even lighter. So if you're going to do some type of shored construction, it's best not to camber. Also spandrel beams supporting facade panels, and also continuous beams with cantilevers. If you have a cantilever, you already have reverse curvature in your beam, so don't induce extra camber. So this is an example, fictitious building from St. Louis that we had in the Solution Center. So you can see there's joist framing on the roof and typical framing the rest of the building. This was actually a study we did in the Solution Center, but I mean, how perfect is this? You're never going to have a building layout with all this wonderful symmetric braces. So this was a laboratory building there in St. Louis, so it had a fairly hefty live load of 100 pounds per square foot, and then superimposed dead load of 20, slab dead load of 50. And then roof loads were less. It had a fairly decent facade load of 850 pounds per linear foot. So this is the floor plan. If you spit this out in RAM and tell it to camber it, this is going to be the section that it picks, a 21 by 44 with a 3/4 inch of camber. So, let's think about how our facade's being attached. If the facade's only being attached at the columns and it can span 30 feet, maybe I can camber that beam. But if the facade's being attached intermittently, finding and placing those embeds and matching it up with the cambered beam is just going to be really difficult. So maybe I don't want to camber those. So if I specify no camber, it's going to jump from that was a 21 by 44 up to a 21 by 83. And our perimeter deflection tolerances are usually pretty tight, so that's a lot of times what's governing this. The roof plan, we had with camber, you have an 18 by 35 with 1 1/4 inch camber. If you say no camber on it, it bumps you up to an 18 by 65. So, I mean, you are going to add a lot of extra weight to these perimeter beams if you decide not to camber them, but it's going to save you money on the labor end and make things a lot cleaner in construction. So kind of summarizing again, I think I went over this on the RAM tab, but beams shallower than 14 inches don't camber. Less than 24 feet in length don't camber. Also beams with a non-uniform cross section like a tapered web, that wouldn't be good to camber that section. Beams with a 1/4 inch web or less, those are the ones going to have issues with web buckling in that RAM. Beams with non-symmetrical loading, if you have beams with point loads on it, those aren't good choices for cambering. Cambering is really just kind of bread and butter for your infill beams with uniform load on it. Beams subject to torsion also wouldn't be good choices to camber. As our bay size increases, so does the economic advantage of cambering. The cost to cold camber a beam varies with length, with depth, geographic location, fabricator, and the amount of camber required. So when I wrote that article in 2006, like I mentioned before, I've seen cambering prices for one simple infill beam varying from $35 to $200. So it varies a lot depending on your fabricator. That hot cambering is, we say, 5 to 10 times more expensive. Terry highlighted that it's really closer to just a solid 10 times more expensive than cold cambering. So they're going to use that on members that exceed their capacity of their cold cambering machines. This is a tool we have in the Solution Center that I want to highlight. It's a floor framing tool. If you know your bay size and want to look and play around with, should I camber, should I not, what does AISC think a good bay frame is, you know your bay length and width, and your yield strength, you do have to input a cost and say, okay, cambering is going to cost me $75, but this will spit out for you economical bay sizes and framing sizes for your beam and bay. This is a totally free download on our website. If you just find steel tools on our website and look for the floor framing. So kind of the key takeaways of this, like I said at the beginning, camber is really an art more than a science. Look at the cost and weight benefits. Consider your floor profiles and consider the effects on connections. And then I just am highlighting my references for this. And then these are our regional engineers across the country. So if you have questions, please get a hold of one of us. But that's my presentation. So I'll answer questions, but thank you very much. I'm going to grab my water, but yeah. Yeah, they might have turned it on.
The idea that we can lose cambering in transportation bothers me a lot.
Yeah?
It means that I'm not getting on the site what I ordered.
This was this topic came up in the last session, so now I know this is a big hitting point. Camber is verified in the shop in the horizontal position. Some people were saying that some people are trying to work it into their specifications or whatever, that they can have it verified in the field. I don't know how a fabricator can possibly guarantee that. I'm lucky enough to have Terry here with me. He's a fabricator in St. Louis. I mean, what would you say?
I would say
Yeah.
I would say it's very difficult. I mean, the only thing that the fabricator can really do is verify it in his shop. And there is some, call it relaxation, due to the camber over time, and usually it's during the transportation time when we're shipping it. It's usually not very much. but you have to have some way to measure it, and it's, for us to try to measure it in the field, we can't do anything about it at that point.
And like, there is that half an inch of tolerance, so if you call out an inch and a half, they're more likely going to induce around 2 inches. So hopefully by the time it goes up, it won't be less than an inch and a half, so.
Okay, so give me some feel for how much, you say maybe a half-inch relaxation, where we're talking maybe
Yeah.
a 40-foot or 50-foot member.
You know, it would depend on the erector. If he unloads it in a very poor manner, he can damage and take some of that camber out too. I mean, it's not just the transportation, it's how it's unloaded.
Okay, so there's handling issues. And it would seem to me that we've talked about the issue of long-term loading versus short-term loading with regard to our cambering. If I can't rely on the camber that's measured in the shop and accommodate for maybe some transportation mishaps, and there's some relaxation, what's happening with that steel after it's been cambered and I put it up and I put it into a library building which has a long-term load? And yes, there may be issues about long-term deflection as a result of the creep. That's what I'm thinking of.
Yeah.
Creep. So, but I'm still losing my camper. I mean, there's no point in even doing it. If we can't rely on what's being put into the camper at the shop, and that it's going to be there a week from now, 2 weeks from now, then why do I bother?
It's a minimal amount that you lose. It's,
I
it's not a
don't think it's
major
a-
amount. Like if you're talking about specifying an inch and a half of camber, it's not 0 when it gets to the site, but it might be a quarter inch less or something like that.
Okay.
Yeah, I don't
An
think
eighth
it's...
inch, it's not a major amount, but it does happen at times. Our experience, and let's open this up to other people, our experience is that we tend not to lose as much camber when you put on the load on it, that the camber doesn't come out, whether it be joists or beams.
Yeah, I mean, have
Let's
you
open
been,
it up
have
to
you
other
been in
people,
a,
what your
have you
experience
been
has been.
burned by losing a lot, or?
I have not been burned by losing a lot, but I've never had it pointed out to me that I've lost camber from what was measured in the shop to what's
possible.
what's been installed.
Okay. Bill, you had a comment?
Well, we've had a survey before, just to verify that the camber's still in after the stuff's erected.
So what did you find? I mean, was it real close?
Well, I mean, it just depends. If there's not camber, you replace, you go re-camber. But if, this way, at least you've proven that the camber is existing after you've erected it.
So have you ever guaranteed what it's going to be in the field?
No, but it's verified that the camber's in it.
Yeah.
So, I mean, you can prove that it's there, and if there's a problem, I mean, we've had 1 or 2 beams out of 500 that may have not had the right amount of camber. So
Yeah.
go re-camber them, and replace them. Normally, it's not a problem.
Yeah.
Our experience has been that we certainly rely on quote unquote standard practice. But what we find is typically the camber has not come out even after the load has been induced, and that creates further erection problems. You know, the engineer specified camber in the perimeter beams, and then there was an elaborate detail for how the brick support edge was supposed to be attached. They have to have that level. What do you want me to do about it? I put the camper in control, they put the floor, the deck on, or the precast slabs or whatever, and now the erector is supposed to attach an angle using the detail you showed, and you want it level.
Don't be shy. Call the engineer and say, let's not camber this.
Well, I understand. But understand the code of standard practice is not written by fabricators. Nobody in the front of the code, see who's on the committee, it tells you how many owners and engineers and architects and how many fabricators, and the fabricators are by far the minority. So this is a code, this is an accommodation of standard practices written by the industry. We're not trying to protect ourselves, we're just telling you, you know, the committee is telling the community, what is standard practice and what is achievable. And with all of the issues of transportation and bouncing the beam on the trailer and how it is handled, and we may or may not have the erector working for us. We don't know how many times the beam is going to be handled in the field or how it's going to be stored, what's going to be put on top of it temporarily in the field. There are all kinds of conditions that the fabricator cannot control relative to cancer. And definitely the statement of Camber is more art than science is a definite true statement.
Okay.
I'm on the opposite side when the engineer says that we did a job recently at Snoqualmie Casino in Snoqualmie, Washington, and we had these big crowds. We had trusses out there that were 81,000 a piece, and they came to a point. And then the infill pieces, the header was like 35 grand to tie them in there. We made the triangle, and the infill pieces said natural camber. Poured the concrete on there, and they ended up having to go back through there and fill up to 2 inches because the beams went opposite with no camber in them. And these are sizable members, 21-inch beams.
So you're saying,
A
what?
lot of them were less than 24 feet, and a lot of them were less than 14 inches in depth.
But they had no camber specified? And so then when you poured the slab, they started to sag, yeah?
Right in the specs or right on the structural drawing, you look at the floor plan, it says natural camber. If there's not a denotation with your C equals whatever, it's C equals natural camber. So what your natural camber is, your 1/8 in a foot or 1/8 in 10 feet, and don't camber anything 24 foot or less, and then a 1/4 inch web, 14 inches or shorter, or 44 inches or greater. And we're fighting with the Snoqualmie tribe about it. They're saying, well, hey, we're not going to pay you for that $200,000 in floor overlay you did. Well, the engineer's saying, well, my calc's working. And you said there's 150 different configurations that you got to pick out which load. So it's just leading me to believe that natural camber is probably not a good deal in that situation because it's opposite of what he was pointing out.
Yeah, I know that there's been specifically on our steel interchange, which is in modern steel, somebody had written in about erection procedures for long span trusses and for cambering long span trusses and when you should attach things and when you should release things and...
But it wasn't the trusses.
Okay.
The trusses came to a point and set on a column on a big pier on top of the parking garage. So you got a triangle and then a big massive header in between and then little graduated pieces, and then it went to typical length and then graduated at the end and typical where it goes through the triangle outside of the main header, making the A-frame out of it.
Wow, I'd have to have you draw that for me.
So each side
It's hard.
it's sad is what it was, but was in essence what happened.
No, certainly if you guys run into something like that, please email the Solution Center. That'll be you would get our AISC's kind of official stance on things. They can't really do design calculations or solve arbitrations, but they should be able to point you in the direction of the right procedure. So that's solutions@aisc.org is that email. So, yeah.
Is there any research or anything that shows that they're actually discrete or time related, or is it just due to handling that it
Over time,
I didn't think that it actually keeps like concrete pieces over time on the road. I'm just wondering if there's any research or anything that shows how the camber is lost.
well, most of it is, the majority of it should come out when you pour the concrete slab. So all the... Are you talking about long losses over time versus just the losses in transport? If you're talking about long losses over time, there might be a little, but most of it should be taken out when you pour the slab. If you're only talking about those losses in transport, I don't know. I just know the rule of thumb that it could be up to 25%. I don't know about research.
That's what not including the expected last.
Yeah.
The other losses that I've talked about, and this 25%, is it because it's bouncing and actually
Yeah.
stressing, or is it
I think it's just from vibration. I don't know if there's a time effect, if it sits for 3 weeks versus 3 months. Yeah, I'm not sure about that. Okay. All right, thank you guys for coming.